The seatbelt and airbag are not there to keep you in the car. In fact, if you could be ejected safely from your car, you'd be pretty safe. If you could just kind of keep going, you'd be a lot safer than if you were in the car absorbing all that energy. No, that's not why it's there. Why is the seatbelt and airbag there?
Keep you from not ejecting not safely. To reduce whiplash.
Nope.
To absorb all your momentum.
Okay, so those of you, you want to keep talking about it? Okay, so keep in mind, this is a little bit smaller than your brain. For some of you, this is the size of your brain, but for most of us, this is, I don't have anything brain size, but this is pretty close. This is pretty close to the size of your brain. When you get in an accident, your fatalities are not your skull hitting the windshield. Your skull doesn't really have much to do with it. Your skull will come back. Your skull will be repaired. You can patch it together either with aluminum or titanium or bone. It'll come back. But what doesn't come back is what?
Brain.
Your brain. What kills you in an accident is not your skull hitting the windshield. It's your brain hitting your face. Your face is the problem. Your face is the problem. So your face is the problem. What happens is you got this kind of half-congealed jello gunk all around your brain, and in a hard accident, your brain goes slosh. And it's fine. That's fine. Keep in mind there's a spine here that connects to the bottom of the brain, and that's what tells your heart to beat. Kind of important to keep telling your heart to beat. Well, here's the thing. If you hit too hard and your brain goes BAM against the front of your skull, then two things happen. One, this part of your brain will die. And two, this part of your skull, or this part of your brain will come detached from your spine. If that happens, you die. Okay? Most people can't survive without their heart.
Probably my nervous system.
Yeah. Yeah. So does that make sense? So what's the airbag and the seatbelt there for? It's to keep you from doing this. BAM! Instead, you go.
Like
Okay. The idea is, if the seatbelt and airbag wasn't there, the brain and the skull would move together, hit the windshield, and go BAM! But if the seatbelt and airbag is there, then what happens is you move forward, you keep moving forward. You know your seatbelt stretch, right? Your seatbelt stretch about 30%. Most people don't realize, like, my seatbelt is really tough. No, it's tough for a reason, but it stretches. In a hard accident, you can actually see the seatbelts will stretch out like elastic. They'll stretch, they don't come back, they stretch out. That's why they're woven. So what happens is the seatbelt airbag deploys and you go forward, the seatbelt starts slowing you down and your brain keeps going forward, but it hits your front of your skull a lot slower. So instead of like, BAM! It goes, wow. Which hopefully, if the impact is long enough, then the force is small enough. Yeah.
Aren't seatbelts like more for like if you're braking during the collision? Or like before a collision or something?
No, they work no matter what.
Okay, great.
Yeah. And modern seatbelts are actually smart. They know how much extra seatbelt to release before, depending on the accident. And the airbags know how much airbag to deploy. Airbags, you should just go boom in front of you. They basically create a big pillow in front of you. Modern second stage airbags actually are smart enough to know how much boom to release. So that's pretty cool. We didn't have those when I was your age. When I was your age, we just had a pillow. We just put a pillow right there. Oh no, we're going to crash. Put the pillow.
Oh no, we're going to
Okay, so if you don't have a seatbelt, your time of collision of your skull and your face is very small, which means your force is what?
Very large.
Very large, right? Your force can be very big. So if you have a small time, you're going to have a big force. You're going to have a big BAM with your skull smashing in front of your face. However, if you have a seatbelt and airbag, then the time to collide is going to be much, much bigger. So your time the force of your brain on your skull is going to be a lot, what? Smaller. Oh, hey, get back here. Smaller. There we go, smaller. Okay. That's why it's there. So, anyway, if you need to write that down, great. If you don't, whatever. Okay. Other questions? Cool. So, wear your seatbelt and drive a car with airbags. Don't be one of these rednecks that drives these ancient trucks, big polluting death
The
machines.
hanging truck.
You were like, I like a car from the 1920s. I'm like, great, please don't hit me. And I don't want to deal with it.
Steel frame to aluminum body doesn't do a whole lot.
Exactly. You're basically in a just a can, and you're just gonna get yourself. All right. So consider the following: a 2,000 kilogram truck is traveling 10 meters per second. What's the momentum the truck is carrying? Which is 20,000.
Okay.
So 2,000 times 10 is usually 20,000. And again, what is the unit for momentum? Kilogram meter per second. Good. So momentum can be arrested if it applies its brakes with 4,000 newtons for 5 seconds, or if it hits a tree with a tenth of a second for 200,000 newtons. Same change in momentum. Same change in momentum. Same change in everything. It's just one is going to move a lot of energy into heat because the tires or the wheels, the brakes will warm up, the brake pads will warm up, and the brake discs will warm up. And one, that energy will be absorbed by bending all the metal in front of the truck. But the momentum change is the same. Boom! I love watching baseball. If you get really good, you can actually see the change in momentum from the back. Look how it goes, boom, and it slows down. Okay. So in a closed system, momentum is conserved, which means whatever momentum exists before a collision, it exists after a collision. Okay? Whatever momentum exists before a collision exists after a collision. Would you like to see a video of one of my favorite collisions? Now this is super pixelated because this is before YouTube. This is quite possibly before you were alive. No, maybe not that late. You were probably at toddler.
You can't get through there. No, I can do this. Just chip out. I can get through there. Just chip it out. No, I can get through there. Watch. Okay. Yeah, you're right. I guess I should have chipped out, huh?
Custom clubs for greater accuracy. Chipshop.com.
I can get through there. Watch. Okay. Okay.
See, why isn't the commercials before our time were a lot better?
Just chip it out. No, I can get through there. Watch. Okay. Yeah, you're right. I guess I should have chipped out, huh?
Custom clubs for greater accuracy. Chipshop.com.
That's my gift to you this Saturday morning, or this Thursday morning. Yeah, this is
I wish it was that.
I've tried to find a higher resolution video of that, and it doesn't exist online. Somewhere the advertising company has the originals, but yeah, I love that video. All right.
We got a
So-
contract done.
Yeah, we love her. We're using it in physics. Give us a better copy.
Oh, that's
So,
sick.
collision elasticity, yes.
Oh, that's
You're
sick.
writing something down? Okay. So, momentum must be conserved at all times. Whatever momentum exists before a collision must exist after a collision. And you better believe we're going to spend a lot of time doing some sample exercises in just a little bit.
So, on the next slide, can we do that 1x thing? On the next slide?
Is that the
Mattress?
The mattress?
Yeah, we should definitely
Well,
do
okay,
that.
if you go to the Naval Academy, you can do that.
Oh, dang.
So that's where they are. That's
I'll
That's
be the
the-
guy that jumps up.
those
and does
people
a-
are in control of the nuclear buttons on submarines right now.
Heck yeah, man. That's what I'm talking about.
So yeah, so
Well, I mean,
I'd be the guy that jumps up and does the flip.
yeah. Okay, so again, collisions can be elastic or inelastic. If they are elastic, energy is conserved in addition to momentum. If they're inelastic, then only momentum is conserved. Okay? In an inelastic collision, only momentum is conserved. In an elastic collision, momentum and energy is conserved. I hope I was saying that right. Let's go to Iraq.
Bro, you want to bring some mattresses to school tomorrow? We're just doing the haul out here.
Totally. Yeah, make sure you have to slow, do some of the friction too. Make sure you got a nice high thread count mattress pad under there.
He got a nice roll, but.
All right.
I've done that before. I can totally do it again.
Just a
Totally
nicely
good.
mopped floor and a really good mattress.
Okay, are we ready to move on?
Yeah.
Some of you are writing everything down, you're just watching the video over and over again. So again, this isn't really wordy, doesn't need to be, but elastic collision, momentum is conserved and energy is conserved. Inelastic collision, only momentum is conserved. That's all you need to know. All right, so here's a diagram. You don't need to copy this down because we're about to do it. So imagine you got M1 is traveling with a velocity, we're seeing it's a positive velocity, and M2 is coming in with a velocity. Which object has more momentum?
M1.
M1, okay? More mass, similar velocity. In fact, this one has positive momentum, this one has negative momentum. So after they're gonna bounce, M1 is gonna chase it, because you found that when a heavier object strikes a less massive object, well, actually this one should actually chase it, but you get the idea. So depending on how fast I zing them up there, and then M2 goes out. So here's some notation. P1, P2. Object 1, Object 2. Object 1 has mass 1, velocity V1, momentum P1. Object 2 has mass 2, velocity 2, momentum P2. Afterwards, we're going to use an F to say final. Okay. That's after collision. For the longest time, we used to use a prime, and sometimes you're going to see, if you get online, you're going to see things that say P1 prime. I think there's actually a couple, maybe in the exercise in the packets too, they use a prime. Prime means after a collision as well. The College Board moved away from that notation because it was hard to see, and they made a little F instead. If you like formulas, there's a formula.
What's the name of this formula?
This formula basically illustrates the idea of momentum collisions. What I like to do when I'm doing collisions is make a momentum table. So what I like to do is make a momentum table. I like to look at everything that's going on with object 1. Oops, that's a small, let's make that one. Everything that's going on with object 1 and everything that's going on with object 2. So object 1 has a mass 1, a velocity 1, and a momentum 1. Object 2 has a mass 2, a velocity 2, and a momentum 2. Make sense? Okay. And then I use the two together to realize that everything in the system is going to be PT. PT is just a sum of P1 plus P2. Cool? All right. So this is how I like to do momentum. You don't have to do it this way. I like to put everything in columns. It makes the world so much easier. Okay, so let's do a simple momentum exercise. In this simple momentum exercise, you have a 6 kilogram bowling ball traveling down the lane at 10 meters per second. Okay, away from you is going to be a positive velocity. Positive velocity. So what is M1 in this exercise? 6.0 kilograms. What is V1 in this exercise? 10 meters per second. So what is P1 in this exercise? 60 kilogram meter per second. We don't have a named unit for it, so we're going to go kilogram meter per second. Make sense so far? Did I go too fast, or are you with me? Good? Okay. All right, so P1 of the bowling ball, we established that. The ball strikes a 1 kilogram pin at rest, causing it to move backwards at 20 meters per second. So let's look at the first sentence and not look at the first part of the sentence and not the second part of the sentence. So the object 2, so object 1 here is the ball, and object 2 is the pin. And what is M2 of the pin? 1 kilogram. What is the V2 of the pin? Careful. It's at rest, exactly. Most pins, most of the time when you go bowling, the pins don't move until you hit them. Most of the time, that's the case. Some of you, like, the pin comes start back, and you're like, hey, it's moving, get it! And everybody starts throwing bowling balls at it. That's when bowling gets really fun. Hey, one came back, let's throw bowling balls at it. And the people are like, oh great, there's like 6 people throwing bowling balls at one pin going anywhere. Anyway, so what's the momentum of the pin before the collision? It's 0, yeah. It's 0. 0 kilogram meter per second. Which means the entire momentum in the entire system is how much? 60. There's 60 kilogram meter per second available in the entire system before collision. Cool? What should I write next? It's not M1. I should write V1 final and P1 final. And I should write V2 final and P2 final. Do I need to write M1 and M2 again? Yeah, ordinarily, when you go bowling, parts of the bowling ball don't end up sticking to the pin. That's usually what happens, so we can just say V1, P1. Where do you go bowling? I go bowling with balls of Jell-O. All right, so what information does the exercise give us? Yeah, the ball hits the pin goes zinging backwards, which is still, is that a positive V or a negative V? It's positive, it's the same direction as the velocity of the ball, so it comes back at 20 meters per second, which means the momentum of the pin is how much? 1 kilogram, 20 meters per second, is 20 kilogram meter per second. So what happened? The pin started with 0 kilogram meters per second of momentum, got 20 kilogram meter per second of momentum. Does that make sense what I'm just saying? Hang in there, Aiden. We're almost done. Okay. So where did that 20 kilogram meter per second of momentum come from? The ball, right? So we had 60 kilogram meter per second of momentum in the entire system. After collision, the pin picked up 20 of that. How much is left for the ball? 40. The ball is left with 40 kilogram meter per second of momentum. So there are some people in the room who can, with a calculator or without, determine how fast the ball is going after it hits the pin. Point something? I'll take that. 6 point something?
Yeah, that.
Meter per something? Meter per second? 6 point something meter per second?
You gotta divide it by the mass.
Yeah, so if the ball has 40 kilogram meter per second of momentum, divided by the mass, and you get 6 point something meters per second of velocity left with the ball.
6.7.
6.7? Good.
Hey, that's something.
It is something. 6.7 meter per second.
I don't want to calculate.
Yes.
You want this?
Um,
No, you can keep that.
if I had my basketball, I keep forgetting to come with my basketball. If I had my basketball, then I could, we could do this. This is actually a lot of fun. So you can do this with, oh, I have a yoga ball too. You can put a yoga ball, put a gerbil on a yoga ball, or a guinea pig.
Oh my goodness.
Some of you are just now realizing what that video is about. That's a guinea pig on a yoga ball.
That's what I thought it was.
He's like, I learned this in physics class.
Did she kill it?
No, it's a guinea pig. I mean, their things are pretty tough. They're all just a ball of fur.
Look at the height.
Yeah. Okay, are we ready to move on?
The death is out of frame, therefore it's
Okay, moving on. So inelastic collisions, in an inelastic collision, the objects become a single mass. Okay, in this class, inelastic collisions occur when an object becomes a single mass. Okay, and it looks like this.
When they move together.
So like, yeah, like when a train couples with another train, it goes, okay? That's an inelastic collision. in this class, we have two types of inelastic collisions because we don't want to do calculus and trigonometry. And they're both going to be linear. They are going to be this kind of inelastic collision, where they stick together. And then the opposite of inelastic collision is a reverse inelastic collision. In a reverse inelastic collision, this happens. Fork will do. Oh, come on. Fork, maybe fork won't do. Let's see. There you go. Okay. So that's called a reverse inelastic collision, where two objects basically burst away from each other. So that's the kind of inelastic collision we're going to do. We're going to do two objects sticking together. Oops. Two objects sticking together. And we're going to do objects bursting away from each other. Cool? All right. So we will do that later. The air track today? Bam!
Oh.
Okay. Yeah.
A bit excessive, but I think it gets the point down.
What do I do with my evenings? I just hang out on Imgur and just download stuff. Okay. So an inelastic collision, if you have two objects of the same mass, they look like that. This is what we would do if we did physics AP. We would actually do two-dimensional collisions. We don't do two-dimensional collisions in this class. We saved that for basically another level of collisions. But there you go. Different mass. We learned about different mass. If a lighter mass strikes a heavier mass, lighter mass usually recoils. If it's heavier mass strikes a lighter mass, it usually chases it. All right. Ball bounce. Ball bounce. If a tennis ball comes in and strikes the wall at 4 meters per second and comes out at 3 meters per second, I have two questions for you. One, is this an elastic collision or an inelastic collision? And two, what's the change in velocity? So first of all, if you believe it's elastic, raise your hand. If you believe it's inelastic, raise your hand. Why do you say it's inelastic?
Because it doesn't come back with the same force.
Yeah, it's lost kinetic